Okay, so we're going to look at parent functions. We're going to go through this kind of quickly because most of this should already be filled in, right? You may not have felt comfortable filling absolutely everything in if you had some questions, but for the most part, this should be filled in from what you had worked on. We are going to, in this space underneath these, add in there some anchor points that are going to help us with our transformations. We're going to do that for the linear as well. I am not telling you that graphing lines is about to get a whole lot harder or anything. We're not going to, you can graph lines the same way you've been graphing lines forever. But at one point, I do want to kind of connect all this together, and so we'll use the anchor points so that we, have an idea of what's going on. So, and we're going to graph them on here. So we've already talked about this one, and this one was easy and way old business anyway. But our anchor points are going to be these three. And up here at the very top, we're going to write AP, and then that equals anchor points so that we don't have to write anchor points all the time, but you know what I mean by AP. Sometimes I'll probably say key points because they're kind of the same thing, but anchor points I think is better because that's where it's kind of anchoring your graph down. So our anchor points here, and we'll put them in little charts instead of having to write out like ordered pairs. When x is -1, y is -1, 0, and 1, 1. Those are our three key points. Okay, we have those three, and then if we have to do transformations, we know what we have to do with kind of those. Those are the three that we just sort of move around so that we can then go back and draw our line. Okay. All right, then we have the absolute value function. Okay. Absolute value function. So the function for this, f of x, is equal to what? Absolute value of x. That's why it's called the absolute value function, right? Names make sense at least. The domain is -infinity to infinity. What's the range? 0 to infinity, right? Do I include the 0? Yes, I do. Do I have any x-intercepts? Yes, that is 0, 0. Y-intercepts? 0, 0. Okay, good. Do I have any extrema? Yes. I got a whole lot of no's last period, but yes. I don't know why. But what do I have? What kind of extrema?
Absolute minimum.
Absolute minimum. And that is at 0, 0. And that is an absolute minimum. Okay. Is it increasing anywhere? Yes. From 0 to infinity, right? Is it decreasing anywhere? Yes. From -infinity to 0. Stop me if you have a question. Otherwise, I'm going to assume you have this, filled out because most of it should be kind of simple for you. In behavior, as x approaches infinity, f of x approaches what? Infinity. And then as x approaches -infinity, f of x approaches infinity. Right. Are there any discontinuities? Nope. Is it even, odd, or neither? Even. Okay. Everybody okay with all that? Alrighty. So then our anchor points, we're going to have 5 of them here. And since this is not my skinny have a vertical one, we're going to do it horizontal. It's the same thing. I prefer them vertical myself, but we'll make it fit better this way. So when x is -2, y is +2. X is -1, it's 1, 0, 0, 1, 1, 2, 2. And we want these key points because when you see an absolute value function, even if there's transformations in that equation or whatever, what the picture that should pop in your mind is this right here, the parent function, so that you can then take this and transform it however you need to transform it, right? All right, any questions on this one? We good? All right. Quadratic. Parent function, f of x equals what? X squared. You should have done quadratics a lot, right? Your domain, good, -infinity to infinity. Range, 0 to infinity. Do I include the 0? Yes. X-intercept, 0, 0. Y-intercept, 0, 0. Any extrema? Yes. 0, 0 is an absolute minimum. Is it increasing anywhere? Yes. 0 to infinity. Decreasing? Yes, negative infinity to 0. In behavior, as x approaches infinity, f of x approaches infinity. And then as x approaches negative infinity, f of x approaches infinity. No discontinuities. And is it even, odd, or neither? Even. Okay, so I want you to look at what we just filled in there, and I don't think I can make them both fit at the same time, but everything we just wrote, with the exception of the function itself, everything I wrote in purple for these two, are there any differences? Or is it all exactly the same? It's all exactly the same. Because these two functions visually are kind of similar, right? It's like, kind of like we just took that one and straightened it out. I mean, they're very different, obviously. There's different things happening. But they have a lot of the same characteristics. And the characteristics of these functions are things that you need to be familiar with as well. So our anchor points are going to help us kind of with the shape, since the characteristics are a lot the same, especially after the transformations happen. Okay, so I have 5 of them again. So I start out here when x is negative 2, y is 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. Sometimes we will actually look at a table of values and transform things that way. Sometimes you just need to be able to get them on the graph or get them in your brain and be able to kind of move things around and have an understanding there. Okay? Good? That's right. Yes, but hang on. Oh, Raphael? Okay. All righty. Any questions on quadratics? You got that, right? You can do those in your sleep? All righty. Then let's look at cubic. So cubic parent function, f of x is equal to what? X cubed. That's why it's called a cubic. Domain, negative infinity to infinity. The range, negative infinity to infinity. Right? Do we have any x-intercepts? 0, 0. Y-intercept, 0, 0. Now, listen to the question I'm asking. Are there any extrema? Extrema? No. Is there something we write here? I know it's kind of a trick question. I didn't intend for it to be a trick question, but there should be something written here. What we write is not technically an extrema, because I should have changed that word, but it is a critical point. So there are no, no max or mins. Excuse me. But what do I have that's important? Point of inflection. Good. Excuse me. So that's 0, 0. We can abbreviate point as PT, but I do not want you abbreviating the word inflection, because, oh my goodness, did I get so many weird things on your tests and quizzes, like point of intention and point of, I don't even know what else, but they were I words, but I kind of knew what you meant, but nowhere close, right? So point of inflection. We don't need to abbreviate when we don't even know what we're saying, right? All right, so is it increasing anywhere? Yes, from where to where? All of it, because the point of inflection, and I've gotten this question a lot about, people are a little confused why that wasn't some sort of max or min. This is the point of inflection that changes the shape, right? A max or a min changes the direction from increasing to decreasing or vice versa. But if you see what's happening here, I'm increasing kind of quickly. I slow down, I hit that point, and then I speed back up, but it's actually increasing the whole time. Does that make sense? So it is increasing from negative infinity to infinity. And if it's increasing the entire time, then there can't be a decreasing, right? So then as x approaches infinity, f of x approaches infinity, right? As x approaches negative infinity, f of x approaches what? Negative infinity. Good. Any discontinuities? No. Even, odd, or neither? Odd. So our anchor points here, we're going to use 0, 0, and we're going to use these two. But then we want another one on our graph, okay, because we actually need 5. 3 is not enough, because I could draw a straight line through that, right? And that's not what we're trying to do. But I don't want to use 1.5 just because I can see it on there. It's okay that I can't see it, because a lot of times you'll have more than just 5 that you can go to on your graph. So your anchor points here are going to be, we're going to do this horizontal again. I'm not going to start at -1. Where would I actually start? -2? And if x is -2, what's y? -8, yeah. And so then -1, -1, 0, 0, 1, 1, and then 2, what? 8. Everybody okay with all that? Yes? All right, good. So then we have the square root function. What is that? F of x equals what? Square root of x. That's why it's called the square root function, right? And so the domain is from what to what? 0 to infinity. Do I include the 0? Yes. Range is from 0 to infinity. Do I include the 0? Yes. Do we have any x-intercepts? Yes. 0, 0, 0, 0. Do I have any extrema? Yes. I have an absolute min. So 0, 0 is my absolute minimum. Oh, I can't even write. Hang on. I don't know what I'm trying to write there. Absolute minimum. Is it increasing anywhere? Yes, from 0 to infinity. Is it decreasing anywhere? No, none. So then we have as x approaches infinity, f of x approaches what? Infinity. Now, going the other way. I've had a few questions about this, like what to do. Does it make any sense to write as x approaches negative infinity? No, because it doesn't happen. We don't approach negative infinity. We actually don't even approach 0. We actually get to 0, right? So writing as x approaches 0, f of x approaches 0, that makes sense, right? I get where that makes sense. And I could actually reason through either way. Either we don't really talk about it or we talk about it at 0. And so this was one of those things that the reason why it's so important for me that you have the real definitions and the real theorems, because those are the things that you have to learn to go back to and read and say, okay, what does it really say? Like, what is it saying there? And in doing that, I realized that on the notes within behavior, I didn't give you the actual real definition of it. And so I wanted to have a conversation with Mr. Ackerman about things like this anyway, and I didn't get a chance because I had to leave. But then I realized I was trying to do what y'all do, which is go ask somebody before I tried to figure it out myself without just figuring out what was in my brain. So I looked it up in the textbook, right? I looked up the actual definition, and I Googled it because, you can word things differently. I wanted to see different wordings of it. And this is what, because my understanding of in behavior bothered me. I couldn't put as x approaches 0. My understanding of in behavior is that it's like literally the ends out there at the infinities where you can't see it, right? And that's what I've always understood in behavior as, and I thought, well, maybe it's like one of those situations where that's the only way I've ever seen it talked about, so I was just assuming that's all you ever did, right? But the definition in the textbook says it's what is happening to f of x as x increases or decreases without bound. So as x increases without bound, yes? Yeah. Does it decrease without bound? No. No, it's bounded by 0, right? And then I Googled it to see a different version of the definition, and it says, it means the same thing, but it talks about it a little bit differently. It says, so it's as, what is happening to the function value as x approaches positive or negative infinity. It literally said that, which is the same thing as without bound, which tells me that do we put as x approaches 0? No. Now, if you did, that's okay, because I wouldn't expect you to necessarily know that. I mean, it took me looking it up to be comfortable with really telling you it has to be one way or the other. The thing is with that, I mean, it's not that big of a deal if we get it a little bit wrong here, because in behavior is leading us into the idea of limits. And when you talk about a limit, you can talk about it from two different directions. As I approach the infinities, okay, so as I approach negative infinity, I can only approach it from one direction, right? And as I approach positive infinity, I can only approach it from one direction, right? I can only approach positive infinity from the left-hand side. I can only approach negative infinity from the right-hand side because I can't get on the other side of it. You with me on that? Can I approach 0 from either side? Yes, so we can talk about limits as approaching from one side to another, because if you look at this, and I think my picture's still up. Oh, I erased it. Dang it. All right, I'll have to redraw it. There was a picture on, you don't have to draw this, I just want you to stay with me. There was a picture on one of your assignments when we talked, or I think on the assignment from in behavior, that looked something like this, or it might have been the notes, I don't know. But it looks something like this, If not, this is a good enough example. And we had to come up with end behavior on that, right? And it threw some people off because you were really bothered by this. Like we weren't talking about that, we were talking about this, and we weren't sure what to do. Well, remember, end behavior is what's happening at the infinities. We don't care about middle behavior, right? We care about what's happening when we can't see it. Because if you think of it this way, if we say that this is at -2, okay? So as x approaches -2, what is your function value approaching? As x approaches -2, what's the y value approaching? Infinity? What about this? It depends on which side, right? So this is one where we'd have to talk about the limits. So as x approaches -2 from the left, y approaches -infinity, right? As x approaches -2 from the right, it approaches positive infinity. Does that see? When you can get from it from two different directions, it may be it could be a graph that looks like this. It could look like that, and then as it approaches 0, they both approach -infinity. I mean, that's possible, but they could also be doing different things. That's the idea of a limit. It's not really end behavior. You with me on that one? So the end behavior is out here where we can't see it, and we don't care right now. We eventually are going to care, but right now we're not talking about what's happening right here. Okay? So I said all that to hopefully help you understand that that's why we're only talking about it from one of the sides. The other part is important, but just in behavior itself, we're not there yet. Okay? We're good on that? It's a little weird, I know. It's okay. All right, so discontinuities. There are none. Is it even, odd, or neither? Neither. Okay, so if you're unsure, remember that you can do f of -x, and it's equal to the square root of -x. Can you simplify this at all? If I pull the negative out, does it come out as a negative? What would it come out as? I. Okay, so I can't make this look like f of x, and I can't make it look like -f of x. That's what makes it neither, right? Plus, it doesn't have y-axis symmetry, doesn't have origin symmetry, right? So our key points here. This one, and this one. We have 0, 0, 1, 1, and 2, 4.
Wait, don't you do 4, 2?
Dang it, yes, 4, 2. Thank you. Good job. You were the only one paying attention. 4, 2, I do mean 4, 2. Pass the test. All right, so this function is related to which function we've already talked about? Which one is it directly related to that we've already talked about?
Square.
The quadratic, right? Because the quadratic. Now, I'm going to draw something in here. I do not want you to draw this because I don't want it to confuse you later. I just want you to look, okay? So the quadratic. Well, first of all, how are they related? How is the square root and the quadratic function related to each other? They're the inverses. To find the inverse algebraically, I switch x and y and solve for y, right? And visually or graphically, what's happening is that reflection in y equals x. And when we did reflections on the coordinate plane, if you reflected anything in the line y equals x, all you did was switch x and y. Well, that's what's happening. Well, when you reflect this, you get this. Again, don't draw this because this will all confuse you later. But you get something like that, but a whole lot prettier, right? That's the actual inverse of the quadratic. The square root function is the inverse function of the quadratic, right? Because when you solve that, that's why you get that plus or minus to get the top and the bottom. Just the positive side is that square root function. So all that is a reflection of that line y equals x. So those are definitely related to each other. Okay. So then let's look at the cube root. Well, cube root is related to which one? Cubic, yes. So f of x is equal to the cube root of x. So if I took this and reflected it in that line y equals x, it's going to reflect up here, then it's going to look like the cubic function, right? Or vice versa. The other ways. So my domain, -infinity to infinity. Why am I in pink all of a sudden? Not that it really matters, but shoot. Okay. -infinity to infinity. Range, -infinity to infinity. x-intercept 0, 0, y-intercept 0, 0. Any extrema or anything I put in this blank? Any critical point of inflection, yeah. So 0, 0 is that point of inflection. Is it increasing anywhere? Yes, the whole time, right? My y values are increasing the whole time. So negative infinity to infinity. And then there are none. In behavior, as x approaches infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches negative infinity. Right? Everybody good with all that? Any questions? All right, any discontinuities? None. Even, odd, or neither? Odd. All right, so our anchor points. Got this one, these two, and then some that don't fit. Right? So our anchor points. We've got so I don't want to start with negative 1. I want to start farther out here. What would make sense to start at? Negative 8. So negative 8 would give me what for a y value? Negative 2. And then negative 1, 0, 0, 1, 1, 8, 2. Okay, we good? Any questions? Awesome. All right, hopefully most all of this was already filled out. If you stop me if you have a question. Otherwise, I'm going to assume you should have been able to fill out some of most of this stuff for sure. All right, so the next one would be the reciprocal. So find that. It's on the top of part 2. So my reciprocal function, f of x, is equal to what? 1 over x. Right. So the domain goes from negative infinity to what? 0. And then union of 0 to infinity. The range is the same, negative infinity to 0, and then 0 to infinity. Are there any x-intercepts? No. Y-intercepts? No. Any extrema? No. No critical points at all, so none. Is it increasing anywhere? No, because the y values are decreasing the whole time, and then jump up here, they're still decreasing, so there are none. So it's decreasing from negative infinity to 0, and then from 0 to infinity. Oh, to infinity. Now, remember how when we did this, that's a 0, we put the unions here, but I told you with increasing and decreasing we don't. And I found out this morning that I was told incorrectly, because people asked me, like, why? And I couldn't come up with a good why. And I wasn't even sure why. And then when I finally got into the why, it's because you should be using it, which makes a whole lot more sense to me. So we're going to fix that. Because it just means and. It doesn't mean we're doing anything fancy with it. I never counted it wrong for you. I just marked it out and told you not to do it. I'm changing that. I'm sorry. Okay? I try really hard not to do those sorts of things. But just put the union in there. It's all good. So now if it takes you a while to kind of get used to putting it back in, I'll give you some grace on that. It's all good. All right? But we do. Because it just means and, which makes a whole lot more sense of why we just use it. I don't... All right, so then in behavior, as x approaches infinity, f of x approaches what? 0. And then as x approaches negative infinity, f of x approaches what? 0. Do you understand why it's 0 and not infinity? Because I heard infinity somewhere. We'll make sure we understand why. Don't just change it and still be confused, right? As x gets bigger and bigger and bigger, y continues to get smaller, but it's never going to hit 0. So the y value approaches 0 from both directions. All right, any discontinuities? Yes, good. Infinite. There is infinite discontinuity at what? X equals 0. And it's always an x equals. Even if it's removable, you don't put an ordered pair. It's an x equals. Is this even, odd, or neither? Odd. Okay. And then we have our anchor points. We actually only have 2. So my anchor points are just going to be 1. But if that's the only thing I have to go by, I actually need something else to help me, right? So what does this graph have that the other ones haven't so far?
Rotational symmetry.
Yes, but some of them have had rotational symmetry. But yes, they haven't all had that. What is it? Asymptotes. Okay. So I have how many asymptotes? 2. I have one right here and one right here. So that's a key feature that we need to be able to identify and visualize when we see that. So our asymptotes are at, what's this vertical one? X equals 0. And the horizontal one? Y equals 0. Okay? So when you go to graph this, when we sketch it, there's a difference between graphing something perfectly and sketching it. Reciprocal, you should have that picture in your mind, okay? Know where the pieces are and everything. And then we should be able to draw in or know where our asymptotes go. And if there's a shift any which way, the asymptotes just go with it. We get that graphed in. And then we get these points. And depending on what's happening with your transformation, well, if during the transformation the asymptotes are here, but this point ended up right here, then that's the only point I have. That's okay, because I know what it's supposed to look like. It's just going to approach that, and it'll be easy to sketch. That's all we really need. Okay, we good? All right. So exponential, we've talked about, right? And but I want to add in there some other things. So we already did all that one, but we have our points here. I would use this one. I would use 1, 2, and I would use 2, 4. But I would also use this one to help me with the shape. Now, this one's a little bit different than that because I had to have a number in here, right? And whatever that number is will change what the actual points are. But your X values change your Y values. So this is what these would look like specifically. When X is -1, what would Y be here? 1/2. Ooh, those decimals just give me the EBGBs. And then the X is 0. What is Y? 1. And then 1, 2. And then 2, what? 4. Okay. So if I changed the base, if the base was 5 instead of 2, this would be -1 and what? 1/5. What would this be? 0, 1. This would be 1, 5. Would this be 2, 10? No. 2 what? 25. This right here doesn't change even when the base changes because anything to the 0 power is 1. Okay? All right. So then I also have an asymptote, right? Got this asymptote right here. That's important for us. So our asymptote is that X equals 0 or Y equals 0? Y equals 0. Everybody okay with that? That's a Y. Kind of looks like a weird G or an 8, but okay. All right, so then we have this exponential as well. What's the difference between this one and that one up there graphically? Okay, growth and decay, yes. And their reflections. Okay, so one's growth, one's decay, and their reflections across what?
The y-axis.
The y-axis. And when you reflect something in the y-axis, you just do what?
You switch the x.
You
Negative.
change the sign on x. Okay. So instead of 2 to the x power, it's 2 to the negative x power, but we don't put the negative exponents, right? So what does that actually become to become a positive exponent? 1/2. Good. So this, when you have that decay, f of x is equal to 1/2 to the x power. And that, again, could be 1/5, whatever, right? So our domain, -infinity to infinity. Range, 0 to infinity. Do I include 0? No, I do not. X-intercepts? None. Y-intercepts? 0, 1. Same thing, right? Because anything to the 0 power is 1. Are there any extrema or critical points? Nope, none. Is it increasing anywhere? Nope, that's why it's called decay, right? And it's decreasing from -infinity to infinity. Our end behavior, as x approaches infinity, f of x approaches what? 0. Okay? As x approaches -infinity, f of x approaches infinity. No discontinuities, even, odd, or neither. Does it have y-axis symmetry with itself? No. Doesn't have rotational symmetry, so it is neither. Alrighty, so then my anchor points, right here, right here, right here, right there. Anchor points, getting me. We'll start out here at -2. So -2 will be at what? 4. -1 is at 2. 0 is at 1. And then 1 is at 1/2. And if that was 1/5 instead, then this would be 25, 5. This would be the same, right? And then that one would change. I also have an asymptote. Need to write that down. Don't flip too quickly. Your asymptote is at y = 0. Okay? Everybody okay with all that? Any questions? Awesome. All right. So now we have log functions. Right? So log of x, right, of some base. And if I don't put a base, what's the base? 10. So this is actually log base 10. So this is just log of x, but the base could be anything that's greater than 1. Our domain goes from 0 to infinity. Do I include 0? No. My range goes from -infinity to infinity. X-intercept is 1, 0. Y-intercept is what? None. Are there any extrema? No. Okay, just checking. All right. Any extrema? No, there are not. So there are none. Increasing goes from 0 to infinity. There is no decreasing. As x approaches infinity, f of x approaches infinity. Does x approach -infinity? No. So we just don't even talk about the other part. Now, as x approaches 0 from the right-hand side, y approaches -infinity, but that's not end behavior. That's middle behavior, which is not really called middle behavior, but you know what I mean. All right, no discontinuities, even, odd, or neither? Neither. All right, so our anchor points. We got this one. And then it would be nice to have another one. What would another one that would be easy make sense? If it's log base 10. What's log base 10 of 10? I'm going to go tell on you to your other two teachers. Log base 10 of 10 is 100. Log base a million of a million is 1. Okay, so it's 1. So we can't put it on the graph, but it's 1. And so then if I'm here, this is a good point for me on this one. If log base 10 of 10 is 1, what do you think would give me a -1? 1/10. Okay, so my anchor points here are this. Okay, oh, let me do this horizontally since it's a fraction. It'll be hard to write. Sorry. I was thinking there was only 3, but I know there's not a whole lot of space there for you. So when x is 1/10, what is y? -1. When x is 1, y is 0. Okay? And then when x is 10, this is 1. If the base changes, then these two things change. This does not. Okay? All right, so then, do I have any asymptotes? Yes, I do. I have this right here. So my asymptote is what? x equals 0. Everybody good with all that? Any questions? All right. Logarithmic again. How is this one related to the one we just looked at? Okay, it's a reflection, though. It's a reflection in the x-axis. So f of x is equal to log base 1/10 of x. So when your base is less than 1, but greater than 0, then it looks like this. If it's greater than 1, then it looks like the log function that you're probably more used to. But even if you weren't sure what to put here, I think you can look at this and still get most of this filled in, right? Your domain goes from 0 to infinity. The range goes from negative infinity to infinity. X-intercepts, 1, 0. Y-intercept, none. Any extrema? No. Is it increasing anywhere? No. Which means it's decreasing from 0 to infinity, right? And then as x approaches infinity, f of x approaches negative infinity. And then do I talk about the other one? Nope, because we're not heading to infinity. Okay, so good enough for us right now. Any discontinuities? No. Is it even, odd, or neither? Neither. Okay. So we've got some anchor points we need here. So at 1, or at 0, at 1 I'm at 0, sorry. At 0, I'm nowhere, right? But at 1/10, I'm at 1, and then over here, right? So again, my anchor points look like this. X is 10. Y. When x is 10, this is negative 1. Okay. Everybody good with me on that? All right. Do I have any asymptotes? Yes, this is important too. So my asymptote is at x equals 0. Okay. Everybody good? All right. Now for this weird thing, which is really not hard. It's just kind of weird. And it's not anything that, honestly, we're going to deal with that much in here. We will a little bit because you need to learn it. But it is something that Mr. Ackerman asked us to put in because you do use it in calculus, and nobody's ever talked about it before calculus. I don't even know if it's something technically I'm supposed to do in pre-cal, but it doesn't matter because it's not hard, and the more you see it, the better off you are. And it looks like it's going to be crazy or weird stuff, but it's not that bad. So the parent function, here's what's weird about this, is you actually don't start this one with f of x. Right? Even though it is a function. Is it a function? Okay, it is a function, but you start it with SGN for signum of x. Kind of weird, right? That's what it is. Okay, so signum of x equals the absolute value of x over x. Then there has to be a little bit of clarification with that, right? Because what happens when x is 0 in here? It's undefined, right? But we have a point. So here's the other weird thing, is that technically that point is there, and there's like a disclaimer with this. When you actually use this in calculus, you don't care about this point anyway, so most of the time you just ignore it, and whatever works there is just fine. Okay, but we're going to make the disclaimer a little bit differently, because you can also write this as a piecewise function, and we're going to do that down here. So your signum of x, and you may not have done a ton of piecewise functions, but basically, do you see how this is in pieces? And if you have any sorts of discontinuities, you can just write about it in pieces. If I just talked about this left piece, well then basically y equals negative 1, right? But not for the whole thing. So you have this bracket has to be kind of big because we're going to list 3 things. So y, or the signum of x, is equal to negative 1, but not the whole time, only when it is less than 0. That make sense to you? When x equals 0. And then it also equals 1, but not the whole time, only when x is greater than 0. So that looks like crazy, weird, and complicated. The function itself is pretty simple. We'll be able to apply some transformations to this. There's not much you can do to it, but you can move it around and you can expand it and whatnot. So we'll look at those things. We're not going to get into filling in the rest of this today because I won't be able to get through the whole thing. Tomorrow we're going to start here and then work our way through the yellow. So I don't want you to fill anything else out on this on your own, but I do want you, and I don't want you to fill anything on the yellow, but I want you to look over it, especially the little chart. If you want to glue the pink ones in, you can. I gave you page numbers for that. Remember when you fold it, to fold it where you can actually read parent functions right here. And if you fold the yellow one, I made sure that when you folded this, you could see transformations reference sheets like this. I graded some ISNs, guys, that people had stuff glued in like this, which means when they open it, they have to flip their ISN around, right? I would be consistent. It's going to make your life a whole lot easier. Always turn it to the left or right. I don't care which way. Just make sure you're not having to flip around your stuff. All right. Have a great day. Go to math time.